Hi, everyone. Welcome to 83rd Stanford MedAI Group Exchange session. This week, we have Siyi Tang from Artera AI here with us to talk about her work on modeling multivariate biosignals using graph neural networks and structured state space models. Most of you already are familiar with Siyi because Siyi was one of the founding organizers of Stanford MedAI Group Exchange sessions. These days, she's working as a machine learning scientist at Artera AI. Her research is focused on developing multimodal deep learning models for predicting cancer patient outcomes and personalizing treatment strategies. She recently received her PhD degree from Stanford University, where she was advised by Professor Daniel Rubin. At Stanford, she worked on developing deep learning models for medical time series data with a focus on graph-based modeling approaches. So, Siyi, thank you very much for joining us today. You're obviously very familiar with the format of this session. Please let us know how would you like to take questions.
Yeah, I'm fine with any questions at any point. Feel free to interrupt me.
Okay, thank you very much. In that case, as always, let's try to make this session as interactive as possible. And without further ado, let me hand it over to Siyi.
Thanks so much, Amara, for the kind introduction. So yeah, glad to see everyone again at MedAI. So today I'm going to present this work, modeling multivariate biosignals with graph neural networks and structured state space models. This paper has been accepted to the conference on inference, health, and learning. And it was also presented at ICLR time series representation learning for health workshop. So this is a work that was done during my PhD at Stanford. So why are we interested in modeling biosignals? Biosignals are a type of medical time series data. They are very important in medicine. For example, electroencephalogram or EEG measures the brain electrical activity from electrodes placed on different parts of the scalp. And electrocardiogram or ECG is also a type of biosignal, which measures the heart electrical activity from electrodes placed on the surface of the body. And many of these biosignals are multivariate because they are measured by multiple sensors placed in different parts of the body. So in addition to the temporal dimension, there's a spatial dimension for these types of data. Biosignals are very important for clinical decisions. For example, EEG is the major test for seizure diagnosis. And ECG is a main test for diagnosing heart arrhythmia, such as atrial fibrillation. So why are we interested in developing deep learning models for modeling biosignals? This is because with the help of deep learning, it could enable early diagnosis of the disease and ultimately improve the patient outcome. However, there are some challenges in modeling multivariate biosignals with deep learning models. The first challenge is that many of the biosignals have long-range temporal dependencies. For example, so a lot of the biosignals exhibit long-range temporal dependencies, and this has been studied in the literature. For example, for an EEG signal, for a 60-second EEG signal that's sampled at 200 hertz, this is equivalent to 12,000 time steps. So if we want to capture this EEG signal, the temporal correlations within this EEG signal, the model needs to be able to capture temporal correlations across 12,000 time steps. This is considered pretty challenging, especially for even for modern deep learning models. And the second challenge is that there is non-Euclidean spatial correlations among the sensors. So why non-Euclidean? This is because most of the sensors are placed in different parts of the body, and this exhibits like a non-grid data structure. So if you can let's look at this EEG electrodes as an example, we can see that the electrodes are placed on the scalp, and the EEG electrodes form a data structure that are not like a regular grid structure like 2D images or 1D time series data. So we call this type of data as non-grid or non-Euclidean data structure. To model non-Euclidean data structure, there's a well-studied data type called graphs that can represent non-Euclidean data. However, this also introduces the third challenge of modeling multivariate biosignals, which is that graph structures may not be easily predefined for biosignals. This is because sensor locations may vary among individuals. Like, for example, for EEG electrodes, although there's a standard EEG placement, basically instructions on like where to put each EEG electrode, the individual head sizes may vary, and the exact sensor locations may be also different because of patient injury or because of some clinical needs. And the second reason is that graph connectivity may change over time. So let's look at this figure as an example. The first half portion of this figure illustrates an EEG without any seizure or normal EEG section. And the second half of this figure shows EEG portion that has a seizure event. So studies have shown that the brain connectivity across channels are more synchronized when there's a seizure compared to a normal state. So we could expect that the graph connectivity actually changes when the EEG evolves from a normal to a seizure state. So in order to address these three challenges, in this work, we propose the corresponding solutions to address these challenges. So in order to address the challenge of long-range temporal dependencies, we leverage structural state space model, or S4, which is a state-of-the-art deep sequence model to capture long-range temporal dependencies. And I will talk about some brief background about S4 later. In order to capture the non-Euclidean spatial correlations, we propose a graph neural network-based modeling approach. And finally, to address the challenge of the fact that graph structures may not be easily predefined, we allow the model to learn dynamically evolving graph structures from the data. So instead of predefining the graph structures, we actually allow the model to learn the graph structures from the data. So before I move on to talk about the detailed methods, I want to give a brief background about a graph. So a graph is defined by a set of nodes and a set of edges between the nodes. Each node can have some node features. For example, let's look at this very simple graph with 6 nodes and 6 edges. We can represent so the way we represent biosignal as a graph is that we could treat the sensors as the nodes in the graph, and signals within each sensor as the node features. And for the edges, we can define the edges based on the similarity of distance or distance between the sensors. So this is a general representation of the general graph representation for biosignals.
So we can discuss this point of similarity versus distance between sensors. Distance seems to be a measure coming from just the placement of these sensors, like are they placed close together or are they far apart from each other? Exactly. But what about similarity? Is it some sort of, you have edge features that you would look for establishing similarity between two nodes?
Yeah, so similarity, it's a very wide, broad definition. So you could basically be based on similarity between the signals of each sensor, and you can, like, for example, you can calculate a cross correlation between the signals or some other similarity metrics. Yeah, so this is I've seen a lot of work in the literature that uses different kinds of similarity measure to define the edges.
Okay, thank you for clarifying.
So now let's set up the problem. First we need to represent the biosignal as a graph. Here we represent each biosignal as a graph. So the nodes are, as I mentioned, sensors, or sometimes we also call it channels or leads. These are just different terminologies. And the node features are the signals within each sensor. And the edges are basically how different nodes are connected. And we can also represent a graph using the graph adjacency matrix, which is basically a sparse matrix of size number of nodes by number of nodes. And there is and if there's connectivity between node I and J, then Wij would be larger than 0. So in our setting, the edges and graph adjacency matrix are unknown and will be learned by our model. And again, this right figure shows an illustration of the graph representation. And in this paper, we focus on biosignal classification tasks, which is basically a graph level classification tasks. Because each biosignal is a graph. So in the end, we want to classify each graph into one of the classes. And here is an overview of our proposed model called Graphformer. It has 3 main components. So the first component is S4 layers that are basically process the raw signals and capture the long-range temporal dependencies in each sensor independently. And then we have a graph structure learning layer to learn the underlying graph structures from the outputs from the S4 layers. And we do some like pruning so that the graphs are more sparse to improve computational efficiency. And finally, once we have the graph structures defined, we pass it through several GNN layers to basically learn the node representations. And then we have a pooling layer as well as a linear layer to basically pool the node representations into graph representations. And then we obtain predictions for each classes. So now I will go into details of this Graphformer. Yeah, before I go into detail, I also want to talk about a brief background about deep state space models and S4. So these kind of models are based on the fundamental state space models, or SSM, which has been the workhorse of signal processing and control theory. And deep SSMs are basically deep learning models that learn the matrices A, B, C, and D by gradient descent. And we can also discretize SSMs. And a prior study has shown that discrete time SSM is equivalent to this convolution. The key takeaway is that we will have an SSM convolution kernel, which is basically a global kernel that has the length of the sequence length. And S4 is a special parameterization of deep SSM with a special parameterization of the matrix A. So this has 2 advantages. The first advantage is that it enables a fast computation of this SSM convolution kernel. And the second advantage is that it is able to capture long-range dependencies up to millions of time steps. So in our model, we basically use S4 as more like a black box model to process the raw signals into S4 embeddings. And then we will use the S4 embeddings basically will have captured the long-range temporal dependencies in the signals. So we will use the S4 embeddings to further learn the graph structures as well as the graph representations. Yeah, and S4 has been shown to outperform prior state-of-the-art models on modeling long-range dependencies. Okay, so now let me go into details of each component of transformer. The first major component is S4 layers. However, if we naively apply S4 layers to the signals, we will lose the graph structure. This is because naively applying it will project the sensor dimension to the hidden dimension using a linear layer. So the graph structure is lost in this way. Therefore, instead, we apply S4 to signals in each sensor independently. And we'll call the outputs of the S4 layers as S4 embeddings. The S4 embeddings will be used for learning the graph structures as well as used as node features for the graph. So the second major component is the graph structure learning layer. The task or the major objective of the graph structure learning layer is basically given a node, what are its edge weights with all other nodes? And this is actually analogous to self-attention. So to illustrate this, on the left figure, I show basically the attention weights of between the word it and all other words in this sentence. And darker color basically means higher attention weights. And similarly, given a node in the graph, it could also have edge weights between all other nodes, and darker color here also means higher edge weights. So we could see that there's some analogy between attention weights and edge weights. So
can I stop here and can we talk about the the dimension, or how do you create finite signals? So you have this multivariate signal input, right? So is there a time limit that this has to be a 60-second signal, or like you have a limit on the number of samples, or do you discretize your or do you create multiple signals out of a longer signal? Let's say you have a longer, let's say, ECG signal. So I mean, how do you create this finite multivariate signal input?
Yeah, that's a great question. So usually we use the signal as it is. Like for example, for ECG, it is usually 10 seconds long. So we would just take the 10-second ECG as inputs. And say if the ECG is sampled at 500 hertz, then the signal, the sequence length is basically 5,000 times that, right?
Okay. So you would have a basically 5,000 step long signal. And multivariate means it's coming from multiple sensors, right? That's it's coming from n sensors, so you have n signals and n multivariate signals. And then your S4 layers, they're going to generate an embedding for each of those n channels or n sensors. So any limit on the dimension of the generated embedding, or is it left up to the S4 layer? Or is it a design choice?
Sorry, what's the limitation of the?
For example, let's say 5,000 times step is the is the dimension of one sensor signal that's coming into the S4 layer. That one sensor is going to act as one node in your graph structure running. So you need some node features, and those node features are coming from S4 layer. So what's the dimension of that node feature? Is it a design choice, or is it handled by S4 layer?
Yeah, it's just a hyperparameter. So this S4 is it can be used like either a CNN. You can think of it as a CNN layer or an RNN layer. So basically, you can define the hidden dimension of these embeddings, and usually it's like 128 or 256. Yeah.
Okay, so it's basically a hyperparameter or a design choice. Makes sense. Thank you.
Right. Yeah. So after we observe this analogy between attention weights and edge weights, we move on to basically apply self-attention to minput S4 embeddings. So while there's an input, minput basically we put it over the temporal dimension of the S4 embeddings. And in addition to that, we also allow the model to learn one graph within each pre-specified temporal resolution. So let's say this entire signal is a 60-second EEG, and we basically predefine some smaller time interval to generate one graph within each predefined time interval. So the reason is that we want to capture the dynamic graphs evolving over time. So instead of learning one graph for the entire signal, we try to learn multiple graphs over time. And we hope that this could basically capture more dynamics in the data. And for the for example, for the first dynamic graph, the adjacency matrix is basically learned using the standard self-attention operation. And we can easily extend this to like multi-head self-attention. And in order to guide the graph structure learning process, and also like borrowed from the literature, we added a KNN graph to the learned graph structure. So the KNN graph is basically defined based on by connecting. So for each node, we connect the top three neighbors based on their cosine similarity in their S4 embeddings. So this is with the hope that it could better help guide the graph structure learning process. And also to improve computational efficiency, we applied graph pruning and to remove the edges whose edge weights are smaller than a threshold. And this threshold is also a hyperparameter. And finally, we also added graph regularization laws, which has been a common way of graph structure learning. So this regularization laws basically encourages the learned graph structures to have to be more smooth and to have more sparsity, as well as discourage disconnected nodes from all other nodes. So the third component of transformer is GNN layers. This is pretty simple and basic. So we basically apply a standard GNN layers to the learned graph structures. And the node features are S4 embeddings from the S4 layers. And in this step, we can apply any existing GNN layers. In our experiments, we use this graph isomorphism network because this model architecture has been shown to be more expressive than other prior model architectures. So once after GN layers, we could apply pooling layers as well as linear layers in order to obtain prediction or probabilities for each classes. Any questions here before I move on to experimental setup?
Yeah, at least one question from my side is that, so you basically from one signal, you're creating multiple graphs, right? For short time intervals, right? So maybe one signal comes in and you get like 3 or 5 graphs in a sequence. Your GNN layers, they are not sequential per se, right? They're independently processing each graph. So you would get representations, node representations for, let's say, those 5 graphs separately. And then you would apply pooling, right? And pooling would give you 5 graph representation vectors, right?
Yes.
And then you're inputting them in the linear layer. I mean, there isn't a temporal or recurrent component from in your pipeline beyond graph formation.
Yeah, so the pooling actually consists of graph pooling and temporal pooling. So we also pool over like the multiple graphs.
Okay.
append one single graph representation.
Okay, so once you get into your results, maybe we'll see how this very significant pooling, how does that affect the results? But let's see. I don't think we have any more questions from the audience, so maybe we can dive into your experimental setup.
Sounds good. Yeah, so we used 3 biosignal classification tasks in this paper. The first one is a binary classification task of seizure detection from EEG signals. And the sequence length is basically 12,000 time steps. So this is based on, we want to classify each 60-second EEG into seizure versus non-seizure. And the number of nodes or the number of EEG sensors is 19. The second task is a sleep staging task, which is a 5-class classification task from these polysomnogram signals. And the sequence length is 7,500, and the number of nodes is 16. And for the last task is we do a ECG classification, which is a multi-label classification task. I believe there are 9 classes in total. So there's 1 normal class versus 8 other abnormal classes. And the sequence length actually varies from 600 to 6,000 time steps. And the number of nodes is 12. Yeah, so we can see that these 3 tasks cover a pretty wide range of sequence lengths. And especially for the EEG seizure detection task, the sequence length is pretty long, and it is actually a pretty challenging task. And I want to stress that we didn't do any pre-processing of the raw signals. So basically, so you might see that in some prior works, people pre-process the signals using like fast forward transform or similar pre-processing steps. So they then might reduce the sequence length into like a much shorter sequence. But because we are using the raw signals, our sequence lengths are still pretty long. So let me show you the results. This table shows the results of seizure detection from EEG signals. And let's focus on the AUROC first. So we could see that, and the baseline models are basically from a previous study, prior state-of-the-art results. And the last row shows the results of Grossformer. So we can see that Grossformer provides 3 points improvement in AUROC compared to a previous state-of-the-art a GNN model that was pre-trained using self-supervised pre-training technique. So I would say this is a pretty significant improvement because Grossformer wasn't pre-trained using any self-supervised task, and it was just trained from scratch for seizure detection. So this table shows the results of sleep staging. And we also compare our model to previous state-of-the-art on the same data set. And we can see that Grossformer provides 4 points improvement in terms of macro F1 score. And finally, in terms of ECG classification, we can see that Grossformer again outperforms the baseline models, which are specialized CNN or RNN models for time series classification. But Grossformer provides 3 points of improvement in terms of macro F1 score. So these are, so far I've shown you the quantitative results. However, we also have some more like qualitative results to show that the significance of graph structure learning. Yeah, but before that, let me show you some ablation studies that we did. So the first ablation study, we aim to show the effectiveness of graph-based representation. So you might say that, oh, since S4 is so good at modeling long-range temporal dependencies, why don't we simply use S4? Why do we want to use a graph plus S4? So the first row here shows basically the results of using S4. And compared to our graph former results, and we can see that these results really indicates the importance or the effectiveness of representing biosignals as graphs. The second row shows the effectiveness of S4 in terms of capturing long-range temporal dependencies. So yeah, in the second row, we basically replace S4 with a GRU gated recurrent units, which is an RNN. However, replacing S4 with RNN basically reduce the model performance by a very large margin. So this demonstrates that S4 is indeed very effective in capturing long-range temporal dependencies. And the third ablation study is to show the effectiveness of capturing long-range temporal dependencies prior to graph structure learning and the overall graph learning. So if you recall, in our graph former, we basically apply S4 layers first before GSL and GNN layers. However, in the third row, we swap the order. So we basically apply GSL and GNN layers first on the raw signals, and then we pass it through S4 layers. However, this also reduces the model performance compared to our original graph former. And the last ablation study is to see the effectiveness of graph structure learning. So for this ablation study, we basically predefine the graph structures instead of letting the model to learn the graph structure. And we observe that especially for the sleep staging task, graph structure learning is actually pretty effective. And we can see that like predefined graph structure actually work pretty well for seizure detection task. And we speculate that this might be because this predefined graph structure is based on a prior study, and it's basically like already well defined based on the geometry of the EEG sensors. So the graph structure might be already pretty good enough to really capture the non-Euclidean correlations between the data. So that's why using a predefined graph structure works already very well for this task. And similarly for the ECG classification tasks.
See, for these three tasks, you have a wide variation in your sequence length, but then how are you dividing them into intervals? Like how many graphs per signal you get for these three tasks?
Yeah, so for this, for the first two tasks, the sequence lengths are the same among the data points. So we can basically, yeah, so we can define the same interval. And currently in this paper, we basically just specify the interval based on some domain knowledge. Like for example, EEG readers usually read EEGs in 10-second interval. Yeah, so we define the time interval to be 10 seconds. Yeah, but I believe that's also an area for improvement and also for future study to actually maybe let the model figure out what's an optimal time interval for each specific task and each specific data type. Yeah, so far these are quantitative results. And I will also want to show you some qualitative results. We actually asked clinical experts to basically analyze some of the graph structures learned by graph former. And the first three subfigures here show the adjacency, graph adjacency matrices of focal seizures, generalized seizures, and non-seizure. So the focal and generalized seizures are basically two subtypes of seizures. And the main difference between these two seizures are that focal seizures is like localized in a certain brain area, but generalized seizures happen in all areas of the brain. So if we take the difference between focal and non-seizure, we obtain this the second last subfigure. And similarly, if we take the difference between generalized seizure and non-seizure, we will obtain this the last subfigure. And we can see that in terms of the magnitude of difference from non-seizure EEGs, generalized seizure is much bigger than focal seizure. As we can see, the colors here are much darker in the last subfigure. So this suggests that the synchronization of abnormalities are bigger in generalized seizures compared to focal seizures. By synchronization, I mean the synchronization among the channels. So this is actually consistent with the literature that generalized seizures are characterized by abnormally synchronized brain activity. And yeah, so this indicates that Grossformer learned pretty meaningful EEG graph structures. Similarly, we can also look at the learned PSG graph structures. This is for sleep staging. So the last two subfigures show the difference between wake and N1 sleep stage. So wake is basically when the person is awake, and N1 is the earliest sleep stage. And the last subfigure shows the difference between wake and N3. N3 is basically the deepest sleep stage. So from the last two subfigures, we can observe that in terms of the magnitude of difference from the wake state, N3 is much bigger than N1 because we can see the colors here are much darker compared to the second last figure. So this indicate this is also meaningful because N3 is associated with slow brain waves that are not present in any other sleep stages. And N3 is also the sleep stage that's most different from the wake state. And finally, we also look at the learned ECG graph structures. So we are only showing some examples of two abnormal ECG classes here compared to normal. And the second last subfigure here shows the difference between this abnormality called first degree atrioventricular block and the difference compared to normal. And the last subfigure shows the abnormality called left bundle branch block compared to normal. So again, we can see that in terms of the magnitude of difference from normal, LBBB is much larger than first atrioventricular block. And this is also clinically meaningful because IAVB is associated with only small changes in the ECG. However, LBBB is associated with pronounced abnormality in the ECG, especially in leads V1 to V6, which are these the leads that have very obvious difference in this last subfigure. Yeah, so this again suggests that Grossformer learned meaningful ECG graph structures. Any question here?
Yeah, I have one question. The way I understand your model, it generates multiple graphs, right? So if you have a 60-second ECG and you divide it into 10-second intervals, so you would get like 6 graphs. So when you are presenting these graph representations, how have you selected a representative graph for LBB or IAVB because or like is it the complete sequence shows that abnormality, or is it just like one graph out of that sequence that shows that abnormality?
Yeah, it's a great question. So all these adjacency matrices I show in these few slides are mean adjacency matrices.
Okay.
So they are average across all the data points or all the samples, as well as all the time points. This may not or we could also like analyze the individual graph structures. However, that's more difficult to interpret. So that's why we started with taking the average of the adjacency matrices.
Okay. Makes sense.
Okay, so in conclusion, we propose a graph structure learning layer to learn dynamically evolving graph structures of biosignals, as well as a model called Transformer, which is a general GNN for modeling multivariate biosignals. Our Transformer achieved state-of-the-art performance on 3 tasks: seizure detection, sleep staging, and ECG classification. And we also show that it learned meaningful graph structures that are reflective of the underlying classes. There are some exciting future directions. For example, currently the graph structure learning layer does not take into account of domain knowledge. For example, domain knowledge of the sensor location. So one potential future work is to leverage domain knowledge to further improve the graph structure learning. And second, we could also investigate more effective ways of combining S4 and graph-based modeling approaches. For example, nowadays, a graph transformer is actually a very popular model architecture. So instead of using a traditional GNN, we could actually combine S4 and graph transformer in some ways. And finally, we could future work can apply this method to other use cases like time series regression tasks. Yeah, so this work is done with my amazing co-authors, Jerry Dolman, Liang Qiong, Khaled, Tina, and Dr. Christy Messer, and Professor Rubin, who is my PhD advisor. And we also would like to thank Stanford HAI and Google Cloud for their support of Google Cloud credits for this work. Thank you. If there's any question from the audience, I'm happy to answer.
Thank you, Siyi, for this interesting presentation. So let's first give our speaker a virtual round of applause. And then if we have any questions from the audience, please feel free to ask. If not, maybe I can start with a question. See, so one of the the drawbacks of using GNN models is generally lack of explainability. So you've done interesting work in diving into the graph structure and seeing how that is explainable, or that. Any thoughts on how you could extend this idea of explainability over the time dimension? Because I understand, especially for if you have longer sequences, longer ECG signals or longer EEG signals. So I understand not all of the signal may represent some sort of abnormality. So if the overall signal is classified to have some abnormality, this might be the result of a shorter subsequence out of that complete sequence. So do you see any explainability work, into explaining this time dimension, like when where on the time dimension is the signal which causes that abnormal classification?
Yeah, that's a great point. Yeah, I do see there are 2 potential directions that we can look into this explainability of which portion of the time series leads to the final prediction. So first could be in this S4, within these S4 layers, because S4 basically aggregates the long-range temporal dependencies. And the second part would be in this portion where we have multiple graphs across the entire sequence, right? So we could potentially look at the individual graphs across time, over time, and see, and try to explain which of these graphs actually represents the disease state and leads to the final model prediction. Yeah. In terms of how I don't know how off the top of my head, but yeah, I believe these are the two areas that we could look into.
Thank you very much for your insight into this. We have no more questions from the audience, so maybe we can end our session today here. And just for everyone, we will be on break for the next 2 weeks, and we'll come back on June 22nd with another exciting speaker. So thank you very much, Siyi, for joining us, and thank you everyone for joining. That's it for today.